Alright, welcome back. Here's part 4 of our lecture. Now before I start though, I want to remind you a couple things. First off, anytime I'm talking too fast or you need to hear something again, let me remind you about that hitting the J key. That is a really easy way to just back up 10 seconds of the video, tap it 3 times and you can hear the last 30 seconds over again. Pretty straightforward. Don't forget too, you have all those mechanisms to get a hold of me. I want to talk to you about these things and so on. In fact, just to be clear, remember, you have just as much right to my time as any kind of other class you could be in, in a traditional format. If you've got questions, I have all kinds of ways for you to get a hold of me, and I want you to get a hold of me, alright? Alright, we're talking about ways in which we might be observing global change in the hydrologic cycle, and so far everything we talked about has been precipitation. Let's talk about some other aspects of the hydrologic cycle that might be changing as a response to increases in greenhouse gases in the atmosphere and so on. And an obvious one to wonder about is snowfall. That would be really interesting and important if we could figure out that there's less snowfall happening because of global warming. That would be interesting and important for all kinds of cloud radiative feedbacks and so on. But maybe because the planet is getting warmer, the air can also hold more moisture. I mean, the warmer the air is, the air could be holding more moisture. Just because it's warmer at the surface, maybe it's colder aloft. The point is, it's complicated. And it turns out, well, some regional studies have shown that there may be some trends in the amount of snowfall that they're getting. Some regional studies have shown that there might be, a larger fraction of the total amount of precipitation a location gets in a particular year is coming in the form of snowfall. All of these are, though, pretty hard to get a handle on. I mean, we don't even have a good theoretical idea as to what to expect. And as it happens, the way the IPCC phrases it, they say that the confidence is very low for changes of snowfall, in particular in Antarctica. You'll often hear people, discussing in the media and so on, how the ice sheet in Antarctica is melting. And then other contrarian opinions will be telling you that, well, but the amount of snowfall in Antarctica is increasing, so it doesn't really matter that there's more melting. The IPCC says maybe, but confidence in that scenario is very low. Okay, how about runoff? I mean, if we are based on theory, thinking that the hydrologic cycle is more active due to global warming and there should be more precipitation, well, we have a really hard time measuring precipitation. I mean, that the rain actually falls where we have a rain gauge and the rain gauge is measuring accurately and so on is actually quite a challenge. On the other hand, all that rain is going to end up in rivers and run off downstream, and we're pretty good at measuring sort of stream flow and so on. It seems like this is actually kind of a way to average out the errors a little bit. Don't worry about how much it rained, let's worry about how much runoff there is. And, well, if there's more precipitation, there would be good reason to suspect that maybe there's more runoff. Runoff in and of itself is important. I mean, it transports sediments and nutrients and so on from the terrestrial ecosystem into the ocean ecosystem and so on. There's lots of reasons to think this could be quite important. And the IPCC does not dispute that this could be important, but the IPCC's job is to tell lawmakers and policymakers and stakeholders what the state of the science is. And the problem is that at the present time, the state of the science says that the observations have very low confidence that there has actually been an increase in the river discharge globally. So far anyway, we're not seeing that. Now, that doesn't mean individual basins aren't seeing increased discharge and so on, but globally, we're just not seeing it yet. And, okay, well, that's good to know. That may be putting some sense as to what our confidence in some of these things are. What about some other components of the hydrologic cycle? How about humidity, water vapor in the atmosphere? Now, we're going to see that it matters as to where that water vapor is. Low-level humidity is one part of the story. Humidity near the surface of the Earth. Now, survivors of ATSEVS533 know there's lots of ways to express the amount of humidity in the atmosphere. Turns out to be, there's dew point, relative humidity, and saturation vapor pressure, and so on. We're not going to get bogged down in all of that right now, okay? We're going to say, hey, if we're talking about the amount of water vapor in the atmosphere, and it shouldn't really matter how we're measuring it, or what units we're expressing it in, or whatever. And, well, it would make sense that if we are in a planet that is warmer at the surface, and a warmer planet, I mean, by Clausius-Clapeyron equation, we know that the warmer the planet is, the more water vapor the air can hold, and since 70% of the planet is a water surface, namely the ocean, there's no shortage of places for water vapor to evaporate off the ocean into the atmosphere and fill up that available space, if you will, in the air parcels at the surface. In other words, the air parcels at the surface can hold more water vapor, and therefore they probably will. So it would make some sense from just a theoretical, hand-waving kind of explanation that a warmer world should be experiencing a trend in which it is also more humid at the surface. And in fact, that seems to be exactly the trend. Again, these are some figures reproduced from the IPCC AR5. And, the bottom panel, for example, shows a time series of about, 40 years or something like that, of humidity data averaged globally from 4 different data sets from different methodologies and so on as to how they averaged it and so on. And the y-axis is specific humidity, which is just one of many ways to describe the amount of humidity in the atmosphere. It's actually the specific humidity anomaly. So we see that originally, back in the 70s, the global atmosphere was drier, whereas in the 2000s, the global atmosphere is more moist. That does seem to be the trend globally. And in fact, if you look at individual locations, now not very much of the globe had enough humidity data from in-situ observations for us to make this work. It's mostly over land and over shipping routes over the oceans. But if you look, where blue means that there's a trend of increasing water vapor in the atmosphere at the surface, and brown means a drying trend where there's less water vapor in the atmosphere, you can see that practically every place on that map there's a blue color there. And in fact, the little stars on there mean that grid point is statistically significant at the 90 or 95, I forget which, % confidence interval. In other words, we can say with great confidence that the amount of water vapor is increasing in most of the world, which matches our theory pretty well. And that's all in situ observations from stations over land or buoys and ships and so on. What about more than just the surface, though? From a point of view of weather and climate, humidity matters lots of different heights of the atmosphere. In fact, what if we just sort of said throughout the whole depth of the troposphere? Remember that word troposphere as in like the lowest, roughly 11 kilometers of the atmosphere or something like that? That's where all the weather happens. And, well, what about just measured through the whole depth of the troposphere, whether in situ observations were taken by like weather balloons and packages of instruments that get carried through the atmosphere, or as we're going to see, there's remote sensing techniques, we can measure the amount of water vapor in the atmosphere. What should we expect? Well, from a point of view of global warming, we know that we expect the surface to be warmer, and the surface being warmer means that the air near the surface should be more moist. But warm air near the surface is also more likely to rise, and there'll be moist updrafts of air parcels rising from the surface because they're warm up into the middle and upper troposphere, transporting that water vapor from near the surface upward in the atmosphere. So it's just sort of in a hand-waving explanation, it would make sense anyway to think that we should have a wetter troposphere as well. Basically, throughout the depth of the parts of the atmosphere where weather happens, it should be wet too. Again, I mentioned that satellites can monitor that. This is actually a pretty cool remote sensing thing that satellites can do. Satellites have a way of measuring the total amount of water vapor through the depth of the troposphere. We'll talk at a later point in the course how that's actually done. It's pretty cool stuff. But like this is an example of what meteorologists call a water vapor image. This is actually a map that the satellite came up with where it used remote sensing techniques to measure the total amount of water vapor in the troposphere, not like at one particular height, but through the depth of the troposphere. It's pretty cool stuff. It gives us a powerful tool to measure the total amount of water vapor in the Earth's atmosphere, and, well, if you look back since we've been doing this, roughly the mid-80s to the present time, I don't think we have any trouble seeing that globally these data sets are showing a positive trend. Looks like we do have an upward trend in the amount of water vapor in the Earth's atmosphere. That's going to be complicated because water vapor triggers a feedback in the greenhouse effect. As you probably know, water vapor is a greenhouse gas too, and it is not a direct forcing of the climate, it is a feedback in climate. It amplifies the effect of the carbon dioxide. So if we have a planet that's getting to have a nice deep layer of more moisture in the Earth's atmosphere, that is a big problem for possibly amplifying the effects of global warming. But that being said, that it isn't the case that every place on Earth has an increase in the total amount of water vapor in the Earth's atmosphere. In fact, if I just show you a figure from the IPCC report, and I'm going to just zoom in on this figure in the Eastern Pacific here. On this diagram here, this is just the same kind of figure we've been seeing before. Blue means more moist, in this case through the depth of the troposphere, and brown means drier through the depth of the troposphere. Well, we see that we actually have areas of very pronounced and statistically significant moistening of the atmosphere kind of along the equator towards Central America. And we have two bands of areas where it seems to be drying. And patterns like that make the atmospheric scientist, the meteorologist in me wonder. They make me pause and wonder, it sure looks like there's more moisture along the equator, and it sure looks like it's drier a little bit farther to the north in the subtropics and a little bit farther to the south in the subtropics in both hemispheres. And hey, that reminds me of something. That makes me think about an old friend of ours from Intro, and that I encounter in lots of the courses that I teach. That's the Hadley cell. Remember the circulation pattern that we've seen in classes like Intro, where there were these circulation patterns in the Earth's atmosphere? See how there's two so-called Hadley cells in the Earth's atmosphere, where they have rising motion near the equator, sinking motion near about 30 degrees north and 30 degrees south? Those Hadley cells, it kind of looks on that moisture map like they're being enhanced. It kind of looks like that rising branch of the Hadley cell near the equator is transporting more moisture upward, and so we're seeing an increase in the amount of moisture in the whole depth of the troposphere. And it kind of seems like we have more sinking motion going on in the Hadley cell at about 30 degrees north and 30 degrees south, pulling dry air from the upper troposphere down deeper into the troposphere, so that the total amount of moisture in the troposphere is less at those latitudes. This really does make us look at this diagram here again and say, seems like a hint. This is making me wonder if maybe my Hadley cells are getting stronger. They are rotating faster, they're pulling more moist air upward near the equator, and they're pushing more dry air downward in the subtropics. And, well, that's going to be maybe a hint of something we should be looking at in the next lecture. But before we go on to part 5 of this lecture, I do want to ask a couple quick questions. Question 9. The observations show that most locations on Earth are experiencing an upward trend in the water vapor content of the atmosphere near the surface of the Earth. The yellow words there, near the surface of the Earth, are the tricky ones. Is that true or false? Make a choice from those two options and get a little feedback before you move on to question 10.